do I? Oh, okay. Well, thank you. I'm Roberto, and this is joint work with my supervisor, Jesper Boos Nielsen, and Thomas Schneider of Darmstadt, TU Darmstadt. The outline of my talk is first I'll introduce very briefly secure two-party computation, whereafter I'll introduce our protocol and give you a very high-level overview of how it works. And finally, I'll present to you some of the experimental results that we sort of measured. So, secure two-party computation is the setting of two parties, P1 and P2, wanting to compute some function on their joint input. However, their input is private to them. They don't want to share it with the other party. So for this, we therefore use this two-party computation protocol. And you can see it as having this setting where you have access to this magic box that will you will forward your input to this box, and then it will compute the function for you, and it will just return the result. And the guarantee that we want is that nothing but the output should be revealed to the parties that don't really trust each other. Now, the task is therefore to sort of realize this scenario using a cryptographic protocol. And it actually turns out that this is a very powerful primitive in cryptography. You can actually express most other cryptography if you can do this secure computation. And this can be seen by all the applications that this sort of primitive have. You can have privacy-preserved data analysis, you can do secure outsourcing, you can do company benchmarking, and you can even do satellite collision detection without revealing your position in space. Let's try to look at one of these applications in more detail, namely secure outsourcing. So let's imagine we have a number of clients, let's say cell phones, and their private information is their location. They're interested in figuring out the proximity to one another, but they don't want to reveal their position to the other cell phones. They can then employ some servers that will sort of help them in this computation. And the way this works is each phone will secret share their input. They will sort of split it in two, and each share doesn't reveal anything about the input, and they send each share to each server. Each phone now does this, and then the servers carry out this secure computation. Without knowing exactly which position they're computing these proximities and just sending them back to the servers, or to the clients. And if at least one of these servers are honest or non-corrupt, then none of the client's info will leak, neither to the servers or to the other cell phones. And well, what does it mean to be honest? In secure computation, we have like two classical security models. We have the SemiHonest, that was also mentioned in the previous talk, where we sort of assume that the servers actually run the protocol as prescribed. They don't cheat. They don't send different messages and so on. And this guarantees that the data doesn't leak if the two servers don't collude or you don't get access to both servers. Now this protects against sort of breaches after the fact. If someone breaks into one of the servers after the computation, this provably cannot leak any information about the positions in this case. And then we also have the stronger malicious one where we have no assumptions on what the servers really are doing, at least if one of them actually runs the code or the protocol as prescribed, then the data cannot leak. And this therefore protects against attacks that happen during the computation. So if someone takes over one of the servers, he cannot learn anything about the data. And as with so many things, we also have security at a price in secure computation. Malicious security is often much more expensive than semi-honest ones, although the previous talk does not have these type of numbers, but in secure computation we usually do. So it's typically a factor 10 to 100 slower to do malicious security. And this brings us to this work. So in this work, we implement the first constant round maliciously secure two-party protocol that at the same time supports function-independent preprocessing. Now, to get back to the example, this actually allows the servers in this example to run up to 90% of the total computation without even knowing the clients beforehand or even knowing the functions that they'll compute. The following sort of function-dependent phase now in this protocol matches the SemiHonest setting for secure two-party computation, so it's much faster. And therefore the client's experience are very improved because they don't have very high latency now. They send their inputs, the computation is very fast, and they get their outputs back. We thereby show for the first time that this Lego primitive for maliciously secure two-party computation is actually highly practical. And if you ignore the cost of this preprocessing, we're actually up to 50 times faster than previous implementations. And if you look at the total computation, then we're within a factor 3. So that's sort of the trade-off that you have here. This work is based on Yao garble circuits. So let's first recall what is a garbling scheme that is like the fundamental primitive. So this is the abstraction of Belar et al. And the garbling scheme consists of 4 algorithms: a garbling algorithm, an encoding algorithm, an evaluation algorithm, and a decoding algorithm. So you start with a circuit C that you initially garble using the garbling algorithm. To obtain a garble circuit F, you have some encoding information E and some decoding information D. You can now take some plaintext input X and encode it using the encoding information to obtain an encoded input, which you can now evaluate on the garble circuit to obtain a encoded output, so to say, which you can now decode using the decoding information to obtain the plaintext output. The typical security guarantee that you get from garbling schemes is that of privacy, that says if you get a garble circuit and a garbled input, and the decoding information, then the only thing you can learn from this is the output. You can't infer anything else about the actual computation. And the most famous optimization to these garbling schemes is the free XOR garbling scheme that basically allows us to not really count XOR gates of our circuit. They're just handled for free. The only thing we really care about is AND gates and trying to minimize those. Those are the ones that really cost. So how do you then do 2PC based on garble circuits? Well, now I just renamed the parties to a constructor, PC, and an evaluator, PE, and now they have their private input X and Y. The constructor will now initially garble the circuit, and then I here sort of assume that you can encode your input bitwise. So if your input is a bit string X, then you can encode your input as either 0 or 1 for each of these bits. You now encode your input. He now encodes this input, and he now sends this over. He sends the garble circuit, the encoded input, and the decoding information. And as you can see, this is exactly what the privacy guarantee gives you, that this doesn't leak anything. Now for the evaluator, we need to use oblivious transfer, as was mentioned in the previous talk, where the constructor offers 2 messages, namely for the input bits of the evaluator, he offers the two messages that will sort of represent this input, and the evaluator picks the one that matches his input. This now allows him to reconstruct a full garbled input that he can now evaluate, and he can decode, and he thus obtains the actual result. Now, this is for the SemiHonest setting, and the current scheme completely breaks down against a malicious adversary. The most obvious attack is if the constructor, he can now garble a different function, say. It's one that might reveal a lot of information about the evaluator's input. And if he does it cleverly, then the evaluator cannot detect this. A more subtle attack is the selective failure attack, where the constructor can set up the protocol so that he will make the evaluator abort depending on his input. So he might abort if his input is 0 for some bit, or he will continue and not abort, but in either way, the constructor will learn some information about this. So the standard way for Yao's garble circuits to handle this is the cut and choose methodology. So instead of sending one garble circuit, the constructor sends many garble circuits. The evaluator will ask to check some of these to make sure that they are correct, and then he will evaluate the rest. And then using some mechanics, you can then sort of make sure that you get a single output that is the correct one. It is not trivial to ensure, but it can be done. And this therefore sort of introduces the sort of replication cost of your computation, like how many circuits do you need to send to actually do this computation. And the state-of-the-art protocols, you have to send S circuits to get security 2 to the minus S. So this already is sort of like a factor 40, a factor 80 times blow-up compared to the SemiHonest, where you just send one circuit. However, there is a way to get around this. Recent protocols take advantage of this amortization technique, where if you consider doing the same computation many times, then you can go below these S circuits, and you can save a log factor in the number of computations that you consider. So this gives you much better efficiency. And well, there is also a third way, and that is the Lego technique. So this was introduced by Nielsen and Orlandi in 2009. And instead of considering doing this cut and choose at the circuit level, they considered doing cut and choose at the gate level. So this is where this asymptotic improvement hails from, where you now get a speed up in the size of the circuit, in a log factor in the size of the circuit. So it works by the constructor, instead of garbling circuits, he garbles a lot of gates. And then we have a mechanism to sort of put them together into a final circuit. And this is what allows the preprocessing to be independent of the function, because you just garble a lot of AND gates. And as I said, this requires a technique called soldering to sort of put these together, and we realize this using homomorphic commitments. Now, the downsides of this initial scheme was that the way that this soldering step was instantiated, we required a lot of public key primitives for all gates of this circuit. So this was terribly inefficient, and it was also not compatible with all the optimizations that we have for Yau's garble circuits. In recent years, we've had a lot of improvements here. We've eliminated these sort of downsides, and we now have very efficient extra homomorphic commitments based on error-correcting codes and oblivious transfer. However, until this worked, the folklore in the secure computation community was more or less that this Lego technique it's asymptotically efficient, there's no doubt about that, but it's not really practical due to this commitment overhead. Which, well, in this work we sort of beg to differ. So that was the outline. Now let's jump into the protocol and how this really works. So we have three phases in our protocol. We first have a preprocessing phase, where the input to the parties is just a number of how many AND gates do we want to sort of prepare for future computations. The constructor will now, as I said, garble a lot of AND gates that using this, and it will just send them over, and it will now commit to the input and output wires of these gates. Yeah. The evaluator will now, just as before, he will check some of them and say, hey, you need to prove to me that these are actually correct. And the constructor does this by decommitting to the input and output wires of this, and then the evaluator can sort of check that this corresponds to what an AND gate would look like. If everything's okay, the evaluator knows that there are not very many bad gates left. I mean, most of them are AND gates. That's sort of the guarantee he has. But in order to sort of handle that nothing can go wrong, he finally sends a permutation over to the constructor saying, we need to stitch all these gates together in the following way so that nothing bad can happen. And this is done using these homomorphic commitments and the soldering, and we now construct these AND buckets that securely compute the AND functionality. This is very parallelizable, and everything so far is independent of the function. Next, we have a function soldering step where the parties actually figure out, okay, we want to do a proximity calculation. So now they learned a circuit, and now the only thing the constructor does is he sort of decommits the values that are needed to sort of stitch these buckets together. So you send the differences between output wires and input wires to sort of form this circuit. And sort of the highlight here is that the data transfer cost in this phase is actually very low. It's comparable, using the previous commitment scheme, it's comparable to sending a single garble circuit. And as opposed to the non-Lego protocols, you actually send all the garble circuits in this phase. Finally, the evaluation phase is actually very similar to the SemiHonest setting. So we still have the oblivious transfer. The keys are transferred in the same way. And also the constructor sends his input keys in exactly the same way, more or less. The evaluator can thus evaluate the circuit, and sort of the highlights of this in this phase is that, well, for this Lego, you only need to send a single set of input keys, while for all the other non-Lego schemes, you need to send one per evaluation circuit. So this is maybe a factor 20 in communication. We also have optimal rounds. It's just a two-message protocol, or a two-message phrase. And in computation, you also don't have to evaluate very many garble circuits. It's around maybe a factor 3 or 4, compared to the others where you maybe have to evaluate maybe 20. So that was the overview, so let's just jump on ahead to the results that we achieved. So first, some general observations. The overhead of the commitment scheme completely dominated our initial phase, so initial preprocessing phase. This takes about 70% of the total time, so we spent great care optimizing this part of the implementation. And this included using very efficient bit matrix transposition techniques, along with using Intel AVS instructions to compute several linear combinations of several hundreds of millions of values in parallel. Now, the results, and yeah, it's clear that the network bandwidth really is the major bottleneck here, as it is for many other 2PC protocols. Okay, so the performance that we sort of measured here, we compare with the AES circuit. So for evaluating an AES, this is like the typical benchmark for 2PC. We compare to two different schemes. We have the Wang et al. Scheme of Eurocrypt this year, and this is in this single execution setting, meaning that it takes about 40 milliseconds to evaluate an AES circuit, and it doesn't really gain anything from amortization. Then we see we have the Rendell-Rosoleg scheme of Usenix last year, and this is this type of amortization where they consider doing many computations of the same kind, so to say. So for one AES, we see that our scheme takes around 100 milliseconds to compute an AES, where we clearly cannot compete with the 40 milliseconds of Wang et al. And this is because there's not enough gates in this AES circuit to sort of get this amortization step. As we increase the number of AES circuits, we see as our scheme becomes better and better because there are more gates, and we see that we can't beat the Rendell-Rosoleg scheme when we consider many AES, but we get fairly close. However, it's more interesting to see what happens if we ignore the cost of the sort of the function-dependent preprocessing, or the function-independent preprocessing. And here we see that the LEGO scheme is much more efficient than the previous ones. We are around a millisecond to compute the AES circuit if we ignore the preprocessing, while the others are, well, the Wang et al. Are at 40 milliseconds, and I think the best timings for the Rendell-Rosoleg is around 6 milliseconds. But this is for this amortized thing. So our source code is online at GitHub if you're interested. And with that, I'd just sort of in conclusion, I would say what we've seen here is that the LEGO technique actually is competitive with the state-of-the-art 2PC, and it even surpasses some of the previous best results if we sort of are in a setting where we can take advantage of pre-processing. Like for instance in this server setting where the servers are going to talk to each other for a long time, they know who they are, so it makes sense to use pre-processing in this case. And with that, thank you.